Yesterday at the end of class, we started talking in a little bit more detail about what happens to charged particles in magnetic fields. We know, and we've known for a couple of days now, that they experience a force, right? These charged particles generate their own magnetic field. There's an external magnetic field. Those two magnetic fields interact with each other to produce a force. And we can find the direction of that force by the hand rule for deflection. You had to use that in today's quiz. Thumb in the direction of the particle, stretched out fingers in the direction of the field, palm points in the direction of the force. We talked a little bit yesterday, though, about the shape of the path of the particle. The particle, when it enters the magnetic field, does experience a force, but that causes it to take a very specific, well-known path. Yesterday, I think I showed you a diagram of a negative particle. Today, we'll make it a positive particle. It doesn't really matter. The positive particle is moving to the right through this magnetic field, this external magnetic field that's pointing into the board. We don't really care what that field is caused by. Maybe it's a couple strong magnets, maybe it's an electromagnet, maybe it's the earth. Doesn't really matter. It's pointing into the board. This positive particle will experience a force that we can predict the direction of by using the right-hand rule for deflection. Right thumb in the direction of the particle to the right, fingers into the page, direction of the field, palm is going to point upwards. So there's a magnetic force in this case that points up. Now, that causes this particle to change direction. It's not going to go straight up because it's already got momentum taking it to the right. But if you're moving to the right and you experience a force upwards, you're going to go somewhere in between. The particle now goes maybe over here. So instead of traveling to the right, now the particle is traveling this way. Well, let's see what direction the force is on this particle now. Thumb up and to the right. Fingers into the board. Palm points up and to the left. So the magnetic force would be this way somewhere. Well, now this particle is going to go this way. It experiences a force to the left, right? Thumb, fingers, palm points to the left. So we've got a magnetic force now to the left. That's going to cause the particle to change direction again. Now it's going over here. Thumb, fingers, palm points kind of down and to the left, right there. We notice that the path of this particle, as long as it's in the magnetic field, is circular. Now, this is only a semicircle, right? But that's only because it's only in the magnetic field for half the time around. We could even experience a path where it's only a quarter of a circle, or a sixth of a circle, or an eighth of a circle, depending upon how long it's in the magnetic field for. As long as it's in the magnetic field, it's moving in a circle. Now, how would you increase the radius of that path? What's one of the things that you could do to change the radius of that path? In other words, instead of having the particle go through like this, maybe you have the particle go through like this and then out the side so that you have only a quarter of a revolution. Nick? Good, that's one way. Have a weaker magnetic field. What's another way? Moving faster. Is that what you're going to say, Brendan? Yeah. Those are the two big ways right there, right? Weaker magnetic field, moving faster. Okay, regardless of how much of the circle is actually followed, while it's in the magnetic field, it will follow a circle. Now, every time an object moves in a circular path, whether it's a car going around a turn, or the Earth going around the sun, or whether it's an electron going around the nucleus, every time an object moves in a circle, it experiences a certain kind of force. What's that kind of force called? Yep, centripetal force. Centripetal force, right? And that centripetal force you learned in Physics 20 is not a fundamental force. It's always got to be caused by something else. In a sense, it's just renaming another force. When a car is going around a turn, friction keeps it in a circle, right? Well, we call that frictional force. We kind of rename it the centripetal force. When the Earth goes around the sun, gravity keeps it in orbit. Well, we call that gravitational force a centripetal force. When the electron goes around the nucleus, it's really the electrostatic force that keeps it in orbit. Well, we sometimes call that electrostatic force the centripetal force. The centripetal force is some other force that points toward the center of the circle. Okay, it's that red force right there that's always pointing toward the center of the circle. We can describe this by the same equation that we have for the last several days. F is equal to QVB. As long as the charged particle is moving perpendicular to the field, and it is in the whole problem here, it's moving perpendicular to the field, then F is equal to QVB. That hasn't changed. But we can now also describe the motion of this particle by the centripetal force equation. Because that magnetic force, we can now call it the centripetal force. Since it's pointing toward the center of the circle, it can be described by that equation. F is equal to mv squared over r. And finally, what you'll often find yourself doing is setting those two equal to each other. If the centripetal force really is just a magnetic force, then we're allowed to set them equal to each other if it happens to work out for us. If it happens to help us solve for what we're looking for, then there's no reason why we can't do that. What I'd like you to do right now is take out your data sheet. I want you to look for F is equal to QVB on your data sheet. Please try to find F is equal to QVB on your data sheet. Yep. Who's got it? Okay, where do you find that? Where do you find F is equal to QVB on your data sheet? It's under electricity and magnetism, right? Okay, it's the very last equation under electricity and magnetism, about 3/4 of the way down the page in the middle. Okay, that's an easy one to find. Now find FC is equal to mv squared over r on your data sheet. Can't find it, right? Because it's not there. It's kind of there, but it's not there directly. On your data sheet, you'll find an equation that looks like this. A is equal to v squared over r. That's centripetal acceleration. You guys know that if something experiences a force, there's got to be an acceleration. If there's a force toward the center of the circle, there's got to be an acceleration toward the center of the circle. And that seems a little odd, right? We're accelerating toward the center of the circle. All that means is that it doesn't mean we're speeding up or slowing down toward the center of the circle. It means delta V. If you did a vector analysis of the velocity constantly changing right here, delta V would point toward the center of the circle. Therefore, the acceleration would be toward the center of the circle. If there's a centripetal acceleration, then there's a centripetal force as well. If acceleration is equal to F over m, and that's on your data sheet as well, and centripetal acceleration is v squared over r, then why don't we put those two together and say F over m is equal to v squared over r. Rearrange that, we get F is equal to mv squared over r. So there's your equation. There's the one that you want. Now you got a couple of choices here when you go to use that equation. You can look on your data sheet and you can derive that equation, F is equal to mv squared over r, like we just did. Or you can remember it. It's up to you. Okay, I've used it so many times that I remember it. I don't check my data sheet every time and derive it every time. But if you're remembering it, one word of caution. Okay, a lot of people, for whatever reason, when they go to write down an equation, especially if they're doing it from memory, they do this. F is equal to mv squared over r squared. Okay, that's wrong. And it'll give you the wrong answer every single time. Where does that come from? I think it's kind of a holdover from doing electric force. F is equal to kq1 q2 over r squared. People get in the habit in our last unit of going over r squared, an inverse square relationship. But that's not the case here. Okay, mv squared over r. We all know that. Okay, we've all used it before, but sometimes we just have those brain farts and we write down mv squared over r squared. Just be careful about that. Okay. Yep. Say it again. No, it applies to every single magnetic field, though. Okay. So the question was, does that apply to every single magnetic field? If the charged particle is moving perpendicular to a magnetic field, it will always be in a circle. Now, you don't always use Fc is equal to mv squared over r to describe it, but you can always use that. Okay, sometimes you'll just use that. Sometimes you'll just use this, and then sometimes you'll use the combination of them. But if it's moving perpendicular to a magnetic field, all three of these at least apply to the situation. You can just use whichever one fits your givens the best at that point. Let's try one. Unfortunately, you're going to have to copy this one down or take a picture of it or something because it's not in your book. All right, guys. It says an electron is moving at a speed to the right through a magnetic field that's into the page. So these are perpendicular, right? And you get a problem like this, they'll be perpendicular. They will. Okay. The only other situation possible is if they're parallel. And if they're parallel, there is no force. There's not going to be any circle if there's no force. So if we want you to do something with this problem, it's got to be perpendicular. The particle is moving at this speed to the right through a magnetic field of this value. We want to find the radius of the path, and we want to find out what direction it goes through. Generally speaking, if you're solving one of these problems and it mentions the word radius, you're probably going to start off with this, FC equals FM. It doesn't mean you can't just use F is equal to QVB or F is equal to MV squared over R. Okay, one of those might be where you have to go with it. But we're at least going to try this first because this is going to work for you 90% of the time whenever you're looking for radius. FC equals FM. That means MV squared over R equals QVB. Now V, I don't know if you notice this, but there's a V on both sides. That means we can cancel out at least one of the V's. Get V squared on the left side, which is the same as V times V. Get rid of one of them. And then cancel out the V on the right side. You don't have to do that, right? You don't have to spot that. If you do, then it saves you some time. If you don't, then plug the numbers in. You'll get it. Solve for R. R has to go up to the top here. So it becomes M times V equals Q times B times R. QB has to go down now to the other side. So it becomes MV over Q times B. And the mass of the electron is 9.11 times 10 to the minus 31 kilograms. The speed, 4 times 10 to the 5. Q is 1.6 times 10 to the minus 19. And B is 2.5 times 10 to the negative 2. Tara gets 9.11 times 10 to the minus 5 meters for that. Now, we're also looking for the direction here, right? The direction that it's deflected up or down. Well, we have a particle, an electron moving to the right. We have a magnetic field that's directed into the page. We don't have to draw this out if you can think of it in your head. Thumb in the direction of the particle, which is my left hand. Okay? Thumb in the direction of the particle to the right. Fingers in the direction of the field, which is into the page. Palm points which way? Palm points downward. So the magnetic force is going to be down the page. Is that good? Is that hard? All right. You guys remember that you have some homework assigned yesterday, due on Monday. It's worksheet number 11. I'm also assigning worksheet number 12, question number 1. That's it. I just want you to get a feel for doing this yourself. So do question number 1 on worksheet number 12, and then we'll take some time Monday to work on some of the other questions. I just don't want you to wait until Monday afternoon to see this again, that's all. So worksheet number 11, all of it. Worksheet number 12, question number 1.